Howdy folks, today we're going to be going over Leetcode problem number 2, add two numbers. This is considered to be a medium problem, so it's a little bit harder than the easy problems. So let's take a look. So the first thing we have our description. You are given two non-empty linked lists. That tells us immediately that we don't have to worry about checking these to be empty, representing two non-negative integers. So we don't have to deal with negatives, which means that they're probably not giving us a way to deal with sign, which is good because in two linked lists containing only numbers, it'd be kind of hard to figure out the sign unless you were doing like a two's complement or something. So they're making it not as hard on us because they're saying, hey, you can assume these are positive numbers, so you don't need to worry about signs at all. The digits are stored in reverse order. That's very interesting. We'll come back to that. No, the other thing is that since we're adding two numbers and they're non-negative integers, we will never have to deal with negative numbers at all. So we don't even have to consider it. That's what that tells us. Each of their nodes contains a single digit. Add the two numbers and return the sum as a linked list. There's actually, this is, I believe, how big number operates. So there's occasionally numbers that you need to store that are too large to store in a 64-bit data. And or like too big to store in a long, stuff like that. So big integer is basically a linked list of numbers. And so looks like we're creating an addition function for that, which is pretty cool. You may assume the two numbers do not contain any leading zero except for the number zero itself. That is kind of interesting. So we can see down here in example 3, we may get numbers that are not exactly the same size. So the idea is they're not going to pad this. So what that tells me is we may run into situations, or in fact we will run into situations where one number is larger than the other and we still need to handle addition of it. So we're going to need to deal with that even though one array is going to be longer. So let's see. You may assume. So this is kind of interesting here. We look at this example, 352 plus 465. How it's represented is 243. So it's represented backwards, right? So 342, it's backwards is 243. This is actually very convenient for us because if we want to add numbers, think about how to do long arithmetic, which is basically what they're asking us to do here. Long arithmetic, you add the ones place first, then you carry over to the tens place, then you add the tens place, and you carry over to the hundreds place, etc., etc. And so then what this means, this is already in the exact order we need, because if we had it in the opposite order, where we had the hundreds place first, we'd actually have to reverse our list or go at it from the top because we need that carry bit to be exact. We need to carry the result of each decimal. Now I know, like you, when I did long addition in school, we started from the right with the ones place and etc., etc. So you can just kind of treat this as if you're doing it that way. Basically, the ones place is the first. Now, this linked list, we show it from left to right here. It's a linked list. It doesn't care what direction you're showing it in. The most important thing is what is first, what is second. And the first element is going to be the ones place. The second is going to be the tens place, whether or not it's from left to right or right to left or top to bottom. So the visualizations sometimes can trip you up here because if you're just visualizing this, you might think, oh man, that number's backwards. I better flip it to put it in the right order. But you don't need to flip it because it's already in the order that we're going to do the addition on. Okay, so they give us a nice definition for our list class here. Each node has a value and then a next, which is just going to be the next node. In the scope, it requires you to understand how a linked list works. So the linked list, like it says, there's a bunch of nodes here. It's not like an array. Most arrays in JavaScript actually are a linked list, but a linked list specifically, it has a pointer to whatever is next in this chain. So if you need to add a new element, you just create a new element and set a next pointer, and you can grow it infinitely. So good choice for something like big number, where you don't know how many numbers you're going to deal with. Down here we see another example. We've got 0 and 0, which obviously turns into 0. This is where they were talking about that not trailing unless the number is 0. I don't think we're gonna need that when we're building our algorithm, but it's still good to know. Then we have down here, we have, what is this, a 7-digit number plus a 4-digit number, which turns into an 8-digit number. So they do not want us to drop anything. So like if this was rolled over to 7 digits, it would just be this. But no, they want us to add that additional digit as necessary. So let's see. Let's just go through and try to add all these to start off with. We're not going to build the singly linked list yet, because remember, this is a series of steps to get our input data towards our output data. And if we just get these numbers, that's a pretty good first step. All right, so let's take a look here. Let's say, okay, I could try to turn these into an array to make them a little easier to work with. I'm not going to. So let's do this. Let's get our first. Let's see. This is probably, yeah, this is a list node. So I'm gonna modify these parameters, I think. So I'm gonna say while L1 or L2. Okay. And what that means is while both of these are accurate, L1 equals L1 dot next, L2 equals L2 dot next. So what that's going to do is essentially loop through the list. And more importantly, well, actually, let's do this. If L1 equals L1 dot next, and if L2 equals L2 dot next. So basically, we're just iterating around on the next pointer, iterating through this, and this is kind of how you iterate through a linked list, because you don't necessarily know how many there are. And so this says, well, if they're different sizes, like here in this case L1, we're going to be looping through L1 next a lot longer than we're looping through L2 next. And that's okay, because we may have a carry bit that we want to deal with, and even if we don't have a carry bit, we still need to grab that output. Speaking of which, well, let's just do it. Let's just print out our numbers, okay? Num1 equals L1 or 0. Oops. L1.val. Let's do that. So what I'm doing here is I'm saying, okay, if we have an L1, use its val as our number. Otherwise, just default to 0, because 0 is a perfectly fine fallback. And 2 equals L2.val. And I'm using optional chaining here to say, okay, only do this, default to the 0 if we don't have a value. Now let's just console log those. Log 1 num2. I'm going to run that. All right, wrong answer. That's fine. At least it did an infinite loop. That can happen if you're using a while loop. Okay, we got 4 and 6. What did they put in? Okay, 2. I would expect. That's not the output I would expect to get. Oh, because I'm doing the next. The reason that happened is because I'm doing the next before I'm actually handling anything. So I want to do the next and after I've processed the number. The reason for that is L1 and L2 start on the first node. So they start on this 2 and 5, and I don't want to skip those. And that's why I got 4 and 6, because I was initially skipping them to the next one and then doing my calculation. So if I run that again. All right, 2, 5, 4, 6, 3, 4. So that works. Let's look at our case 2. We just got 0, 0. Totally fine. Case 3, 9, 9, 9, 9, 9, 9, 9. And then we got 9, 0, 9, 0, 9, 0, which is fine because the last 3 digits of this don't have any match in L2. So this is already working out pretty good. So now what we've done is we've transferred our 2 linked lists into pairs of numbers, which we can then add together. Sum equals num1 plus num2. Okay. Let's look at sum then. No, I don't want to. Just auto-save. I always save by default. All right, 7, 2, 7, 10, and 7. 7, 10, 7. But the thing is, this is supposed to be 8, this last one, because we need a carry bit. And that actually becomes really important for case 2, where we've just got a bunch of 18s, which should become carry bits to go over. So, how do we handle a carry bit? Well, first of all, we set it to 0 each time. Now, there's a couple ways we can handle this. What I would do, the easiest way is to do modulus. Well, yeah, because let's say if you have this, well, no, yeah, because if you have 1 plus 18 here, you don't actually want a modulus, do you? You just want that second digit. So there's a couple ways of getting the second digit. The easiest way is, let's say let me just show you in the comments. Let's say we take 18 here. We divide it by 10. And then we call the, not round, we call floor. And what floor does is it basically chops off the decimal. So that way, if I had something like 25, it would go to 2.5. and then it would cut off the decimal and become 2. So that's kind of a cheap way to get a tens bit. So then I could say carry equals math.ceil, or floor. Floor, again, takes it down to the lowest to first integer and removes the decimal. Sum divided by 10. Then if somehow we manage, well, I guess the highest we get is 9 plus 9, which is 18. So we actually ever would end up with a 1. That's the highest we could ever do. Though I guess we could get a carry built up and maybe get 2 somehow. Anyway, there's a carry, and then we actually have to add that in to our sum, because the sum is going to be number plus carry. And then let's just print out our carry as well. Okay, 7, no carry. Then this 10, oh no, that's the other thing. We actually, our sum actually needs to remove our carry bit. So actually I'm going to minus equal carry times 10. What that's kind of going to do, assuming our example again, we have 18, our carry becomes 1. It basically becomes 18 minus 1 times 10, which equals 8, because that's the actual digit that we want to put into the math. And then the 1 goes on to be a carry. So you can see kind of we're basically doing the same operations as we would do in long addition. It's just we're doing them automatically. So what do we get now? All right, we have 7, carry the 1, we have 8. That's 7, 0, 8. That's what we're supposed to have. This one just becomes 0 pretty much, and that's totally fine. See, we just handled that case. It didn't really matter to us that there were no zeros. Now this one we get 8, 9, 9, 9, 0, 0, and then at the end of this there's that 1. So what we're going to need to do is at the end of this while loop we're going to need to deal with the carry bit if it exists. I keep saying carry bit, the carry number, because that needs to be appended onto the end of that list. Okay, so now what we have done is we've created a list of numbers. Except we're just printing them out. We're not actually putting them in a list yet. We need to turn them into list node. And so what they want us to do with list nodes, what they're probably going to need us to return is the head. The thing is, list node, we have to know what the end is as well for the next pointer. So we need to know where we started. So we need to keep track of that node. But we also need to keep track of whatever our current node at the very end is, because we're going to be appending onto that. So what we're going to do in linked list, this is called the head and the tail. And actually the tail, depending on how it's set up, the tail is actually the part that you, well, I'm actually not sure if you add onto the head or the tail. Let's look that up. It doesn't actually matter. Oh, add to the head. Okay. So you just add to the head. So then what that means is the tail stays the same. The tail is what we return because we go from the tail upwards, and then we're going to push onto the head. It doesn't actually matter. You could reverse them. It's totally fine. It's just nice to be, consistent with this stuff. As long as you return the appropriate one. So what I'm going to do is I'm actually going to set the tail equals new list node. And I'm going to set it to, I'm going to start off with null and null. Okay, I'm just going to give it 2 nulls because I don't know what the number is going to be. Then head is going to be the same tail. Okay, so I've set them, this actually needs to be let. I've set them equal to each other. This means because of JavaScript, they are set to the same memory location. So if I modify head, it will modify tail, which is fine. So now what I'm going to do is down here, this is where it gets a little confusing. I need to turn this sum and this carry, well, not the carry, but this sum into a linked node. So what I'm going to say, let's see here. There could be an edge case here, but let's see if we can figure it out. We're going to say head.value equals sum, and then head.next equals new linked list node. Null, null. All right, and then what that does is every time we compute a value, it sets that value to our current head and then makes a new head on top of it. So we're kind of pre-creating the head. This is going to actually cause us some problems, and I'll show you why. We then return the tail. The reason we return the tail is because that's the starting point of the list, and we need to run through it. So if we run this, I'm pretty sure this is not going to do what they want. And I'll show you why. Oops. Oh, this output is completely wrong. Head.value equals sum. Oh, it's val. That's why, not value. So it just wasn't setting it at all. That's exciting. Let's try that. Okay. Output 8-0. Not really what we wanted. So let's see. Head to because I need to. That's the other thing. I need to reset my head. So I need to advance the head. Otherwise, I'm just going to keep rewriting the same value on the same node, and then there's only one next. So head equals head.next. This advances that pointer to the next node, so it's ready to go. Okay, let's see here. All right, now this is what I was thinking. 7, 0, 8, and 0. That's the problem. So the problem here is that we're creating a new list node every time, right? We're pushing a new list node onto the stack. And that means that we have a 0 at the very end. I don't really want that. So what I can do here is I could actually put all of these numbers into an array, the sum, and then build the list node off of that. But what I'm going to do is a little different, okay? I'm actually going to set these both to null. Then I'm going to have a case in here. Okay, I'm going to say if, not tail, then tail equals new list node, sum, head equals tail. Okay? Otherwise, so this is our base case. If the first time this loop runs, we have no tail. We're guaranteed to have no tail because we set it to null. At that point, we're going to create a new list node. Okay? And then actually, yeah, no, that's fine. Let's do that. And then otherwise, we're going to say head.next equals new list node, sum null. And then head equals head.next. So what does this do? This basically only creates the list node when, rather than pre-creating it and then populating it, which ended up with us having an extra one, this is going to post-create it. This is going to start with null, completely 0. So if they give us empty, which they specifically said they wouldn't, which is why we can get away with this, then we have null tail, null head. The first time we go through the loop, there's no tail, so we create the tail with a null next. Because, and then we set the head to it. The next time we go around the loop, we're creating and setting that next to the next sum. So we're only creating now new nodes when we have a sum to put into them. So we can cut off that 0. So now if I run this, all right, case 1 now succeeds, 7, 0, 8, because we're not getting that 0 on the end. Case 2 also succeeds because we have only 1, 0. Case 3 does not succeed because we're missing that 1 on the end. What we need to do down here is we say, okay, after that loop is done, if our carry is above 0, which means we actually have a carry bit, that means we need to create a new column. And in that case, we're basically just going to do the same thing. Since the head is already set to the next pointer, we're just going to set it to the carry. We don't actually have to advance it here. It's just, nice. So that just pushes that carry onto that list. And now you can see that case is successful. So what did we go through here? Basically, while we have any available numbers in either loop, we kind of pop them off. We get those numbers. If we don't have one, we do 0. If we ever end up with 0, 0, they're both not going to be set, which means that the loop ends. Or if they're both 0 at the beginning, that's fine because all the numbers are 0. Then we calculate the sum and the carry bit. The carry bit sticks with us per loop because we need to add it on to the previous sums. Then, if we have no tail, if this is the first time we've gone through the loop, if we're doing a for loop, we could also use an index, but this is a perfectly fine way of doing it in a while loop. Then we set our initial tail, our initial node on the list, and set our head to that same point. So they're pointing to the same place. The next time around the loop, they diverge. And then they slowly continue to diverge. The tail stays the same. The head continues to increment as we push new sums. at the end of the loop, finally, while we're done computing, we advance our other loop. So we're actually dealing with 4 pointers here. 2 pointers are for the initial 1 and 2 numbers, and those continue to advance along. 1 pointer is the tail, and that stays exactly where it stays. The other pointer is the head of our sum, and that moves. So basically, we've got our 3 pointers are kind of advancing in unison. As we compute the sum, we move along. We compute the sum, we move along. And then at the very end, if we have a carry bit left over, we just append that onto our sum because we need the extra digit. So yeah, that is how, let us submit this. See if they're going to run any other weird tests. No. And you see, that's not great for memory. You could do better with memory, but it's solidly in the middle of response. And this particular solution is O of n. It's because basically you have L1 and L2 are different sizes, could be different sizes, but whichever one is bigger, that's how many times you're going to loop. So it's O of n, right? You're not looping O of m plus n because you're not looping over one then the other. You're just looping over n times, where n is the bigger of the two lists. So anyway, I hope that was helpful, and I'll see you all next time.